talking about. Alright, so for this next test, I know you've been waiting for it. You've been all excited about it. You said, give us the F test, Jay. I'd love to give you the F test. The F test is pretty straightforward. It's what happens when, I mean, if you've been playing along here at all when we've been talking about these tests, you're like, wait a minute, Jay, you tested two populations, you tested their means, and you tested their proportions, but you didn't test their variances or their standard deviations. So what we're going to be testing is the variance or standard deviation between population 1, let's say, and population 2. So maybe we'll claim that there's no difference in their standard deviation versus, well, there is. Make sense? So that's what this test is going to be about, and whether it's variance or standard deviation, either one, the test is the same. We're going to compute, wait for it, an F statistic. I've never heard of it. Well, it turns out that the F is kind of the kissing cousin of the chi-square. Well, it looks very similar. It does look similar. But instead of having 1 degree of freedom, it's got 2. And so to make the F, you're going to do one of the S-axes, one of the sample standard deviations, squared, so sample variance, over the other one. Now, in theory, either one can go on top. In theory. Now, your book, and I think rightly so, always puts the bigger S-axis on top. Now, what that does is it forces it to always be on this side of the distribution. Now, the reason for that is because the table in the back of your book only gives this side of the story. Some books in the old days would have it so it was easy to find both sides, and in theory you could find this other side too. It's just, it makes it harder. So your book just makes it so the bigger one goes on top, ergo it's just this upper side, and voila, you're done. Okay, it's very straightforward. Now you'll notice that none of the calculators have I shouldn't say none of them. The TI 83s and 84s do not have where's my thing? They do not have an inverse F. Only the 89 does. And so I will demonstrate that right now. The other ones do have an F distribution, or an FCDF rather, which we will actually use to find p-values with, because I think that's a fairly fun way to do it. And this dumb computer doesn't want to work with me, so whatever. Alright, so again, it's in here. Apps, Flash apps, stats list editor, edit baby, whatever. And then we're going to go to second F6 for the test. Oops, not the F6. I'm sorry, I lied to you. I'm going to go F5, inverse F. Okay, this one has it. And you'll notice it asks for 2 degrees of freedom, 2 different degrees of freedom. Okay, as you would imagine it would. Okay, so that's kind of how the story goes. We're always going to make this statistic. However, what I want to talk about is well, what happens if I can show you on the charts, and I will, how to find this cutoff score. And I'll use the 89 to find it for the other one, and I'll also show you in Excel how to do it. And that's all fine and good, but honestly, I think it's easier at this point to say, that's too much work to find that critical value. I think I'm just going to find the p-value instead. Okay, so here's what's going to happen. I think that the variance of machine 1 is bigger than the variance of machine 2. And why do I think that? Well, because I run these machines and I see what's coming out of them, and I think that there's more slop in machine 1 than in machine 2. Okay, it's bigger than machine 2. And so what I think is, to me anyways, it sure feels like I said this. The variance of 1 is greater than the variance of 2. And of course the opposite of that is, well, this thing. Right? Nice. And so what do I do? Well, I take a sample. That's what I would always do. And so, okay, for machine 1, we take a sample of, I don't know, 15 things, 15 items coming off of it, and I find that the standard deviation from this sample is 9.2. And from machine 2, I take also 15, and I find that the standard deviation is in fact 7.9. Okay? So my F statistic is literally this easy, 9.2 squared over 7.9 squared. If you like it better this way, you can also divide first and then square. Whatever makes you happy or makes me. Whatever makes you happy makes me happy. Okay? 9.2 squared divided by 7.9 squared. So is 1.35. This is my test statistic. And as I say, I'm really not going to do anything with the inverse charts or anything, or define a critical value. I'm not going to do that for this test. I find it's just way easier to go and find a p-value. To me, that just makes so much more sense. This is a one-tailed test, so I'm going to use the FCDF. Okay, that's it. That's all there is to this. I'm just going to do FCDF. And my lower value is 1.35. My upper bound will always be infinity. And that's because we follow the book's instructions to put the bigger one on top. So we're always in that upper tail. Now the degrees of freedom is n minus 1. Okay? So it's 15 minus 1 and 15 minus 1. In this case, they're both 14. And that won't be true on the next example. And for the most part, they won't be true in the books because they like to see if you're paying attention. And you will see this is a one-tailed test, so my p-value is 0.29. My p-value is 0.29. Okay, well, I didn't even give you an alpha, but the biggest alpha we ever use is 0.1, for goodness sakes. And so since p is greater than alpha, our decision will be to fail to reject H0. Okay? And what does that say? The variance of machine 1 is not significantly greater than machine 2. Okay? It's just not. That's it. You could say that so-and-so believes that Holly believes the girls have a lower standard deviation on her tests than boys. And again, doesn't mean they're better, just means they're more consistent. Okay, so that's what I heard Holly say. I heard Holly say this. I heard her say the standard deviation for girls is less than the standard deviation for boys. And that's fine, but that looks like a what tail test? It looks like a lower tail. But Jay, I thought you said these were always upper tail. Well, you know I did. Because this can be rewritten as this. And for the purposes of this class, it's better to write it this way. Because when you write it this way, and then you go read the book, and you're like, well, why is the book doing it that way? Well, it helps you to get an eye for what's going on here. Okay? So in other words, I can actually do it both ways, and when I'm doing it with the p-value, it's not terribly important either way. So this one will be over here. This one would be over here. But again, I want to teach it only one way, because to me that makes the most sense. So I'm not going to teach it this way. I'm going to turn this lower tail into an upper tail and do it this way. Okay? And so here we go. So she takes a sample, obviously, the men and the women. And she samples 17 boys, and she finds that standard deviation for them is 20, which is ridiculous. And 13 girls, and she finds the standard deviation is 14. So the F statistic is 20 squared over 14 squared. which is 400 divided by 196. So 2.04. Okay. And so, again, that is the critical value right there, but I'm not going to go find it. I'm just going to go find, you see, the F CDF for this thing. And again, the process will be the same every time, which, I like that. There's a lot less messing around. Now, there's always more than one way to do these things. Of course, I've done it about 100 different ways over the years. This, to me, is just the easiest way for everyone's on the same page. So from 2.04 to infinity. Now, the degrees of freedom for the numerator, that's the boys, that's 16. And for the ladies, it is, I forgot, let me look. It's 12 for the ladies. Okay? And so I do this, and I get 0.108 for a p-value. P is 0.108. Now, I didn't pay attention. Did I say alpha 0.05? I didn't, but let's just say I did. Let's say the alpha was 0.05. And so because P is greater than alpha, once again, we are failing to reject H naught, which of course means that Holly's wrong. And what does that mean when she's wrong? That means that the standard deviation for boys is not significantly bigger than for girls. Now, if you're weird and you want to say it the other way around, the standard deviation of girls is not significantly less than boys, that's totally fine too, because it's the exact same thing. Okay. All right, let's do a two-tailer. Mr. Fredrickson believes, let's say, there's no difference in the standard deviation of time spent studying between boys and girls. Good for him. So I heard him claim a two-tailed test. I heard him say this. I heard him say there's no difference. You might have heard it the other way around. You might have heard girls first and then boys. It is really zero difference. Okay, because literally that means there is no difference. I mean, that's what it's saying. There is no difference. So there it is. Now, so what does he do? Well, of course, he wants to test it at something. Let's do 0.05. Okay? So what does he do? He takes a sample of boys. How many? I don't know, 19. And he finds that the standard deviation of this sample is 3.6. And for the girls, he takes a sample of, because he wants to, 21, I guess, and he finds that it is 4.7. So, notice that the girls are bigger this time. See, that standard deviation is bigger this time. So this time I'm going to put my F on top. I'm going to put 4.7 squared over 3.6 squared. Again, our picture, if you need a picture to go along with, is this guy right here. That's what we want. And again, we're putting 0.05 out here. But we're not going to go find that critical value because it's not that big a deal to me. I just want to find a p-value for this guy. And so 4.7 squared .78. Now this is a big deal. This is a big deal. I lied to you a little bit here, I just realized. That should have said what? This is a two-tailed test, correct? It's a two-tailed test because he said there was no difference. It means I'm putting 0.025 in the upper and 0.025 in the lower tail. But by putting the bigger one on top, I'm always putting it on this side. So the question will be, is it here or is it here? That's really the question, yes? And so let's do this. Now the only tricky part to remember, and I mean literally the only tricky part, is that this is a two-tailed test. So when we get done here in a minute and we find our degrees of freedom, I mean our what seemingly is our what is seemingly our p-value, we need to remember to multiply it by 2. So for the ladies, there were 20 degrees of freedom, because that's the numerator. And for our denominator degrees of freedom, it's 18. Oops, stop it. It's 18, I said. There we go. And so we're going to get this number here, which is 0.11. You see that? So our actual p-value is 0.22, which again is bigger than 0.05. So our decision is to reject, or fail to reject H naught. And again, by failing to reject H naught, what are we saying? We're saying there's no difference. There is no difference between sigma for G and sigma for the boys. Okay, boom. Done. That's it. Alright, now, interesting to note. Okay, that's a pretty easy setup there. Can you show us how to do it in Excel, Jay? Well, you know, I'd love to, because that's what I do. Here to help people. By the way, if, or not if, there will be a TI 8384. I didn't steal it, by the way. Just something went goofy when I changed. My hard drive crashed on this laptop, and I transferred it with another laptop that I had. Both had the same programs on it. What? Now it doesn't work. Whatever. I will also be making, that's what I started to say, I will also be making a video for the 8384s as well. So I can do inverse F, for instance. I can do that. I'm going to put in 0.975. Okay, this will give me the upper one. The degrees of freedom would have been, there was 20 girls, and there was, I forget how many boys we had on this last one here. There was, how many boys? So 18 degrees of freedom for the boys. Oops, I lied to you. Oh, that's right. No, that's right. Boom, done. And so this is my upper bound, 2.55. And if I wanted to find the lower bound, it would be equals f dot inverse, right, of 0.025. That's the lower tail. And then, of course, 20 and 18 again, I think, right? And so those would be those two cutoff values. I will never use that lower cutoff value because I'm always putting the bigger one on top. Okay, but I'm just saying you could do it a bunch of different ways. Anyway, fdist is how I would find it for this guy. And here's the thing. Excel only gives you less than. It only gives you the amount less than. So because this is always an upper tail test, I'm going to have to do 1 minus if I'm doing it in Excel. Okay? Just for this F test, the way I'm showing you. So it was 1.78, I think. Is that right? Yes. And then 20 degrees of freedom, and then 18 degrees of freedom, and then 1. And there's that 0.11 business, and then so it's just that times 2. Oops. Oh no, what happened? Oh no. Huh. Times 2. There we go. Done. 22%. Okay? So I will do a follow-up with the 8384, but again, I'm only going to use, for this class, I'm only going to use p-value for the F statistic. If you are a person who feels that they like to use the charts, I will take 1 second here and show you what the chart looks like, just so you're comfortable with it. Okay, so in the back of your book you will see there's actually 3 or 4 pages of these. One for, you see 0.1 up here, you see that? One for 0.05, and then one for, you know, 0.025, and then for one for 0.001, or 0.01 rather. And then maybe one more than that, yeah, 0.001. Okay, so let's just say we're on this one here. And so we had how many degrees of freedom? This is for the numerator. And then this side over here is for the denominator. So we had 20 and 18, you'll recall a minute ago, right? So this is what you would do. This is old school technology. Boom, right there. 2.55 would be your critical value. And then so over here, this is what you'd do. You'd write 2.55 right here. And because 2.55 is right here and 1.78 is right here, you fail to reject H0. The tables weren't set up to do this side. You can dink around with them and find this side, but you get away with that if you always put the bigger one on top. You don't have to fool with it. Okay? So it's pretty straightforward, and I want you to simply use the calculators and use just p-values for these. That's the way I want you working it. Okay? All right, maybe one more here. Hector, what does he think? Hector, yeah, yeah. So there's more believes there is more variation in I don't know. Wait time at Albertsons versus, I don't know, Whole Foods. I have no idea. I don't know that I've ever been in a Whole Foods. Whatever. Okay? So that's what he believes, and he said variation. So he said, I heard him say there's more variation at Albertsons. So the variation of Albertsons is bigger than the variation from Whole Foods. That makes this an upper tail test already, because that's how he phrased it. So I don't have to screw with it at all. And I'm straight up going to go right here, right now. So it's the S of A for Albertsons over the SW there, and I'm done. Okay, for the Whole Foods. So what does he do? Well, he takes a sample of 20 at Albertsons, 20 people. How long did you wait in line? Well, the standard deviation, oops, not the standard deviation. The standard deviation of the sample, that is S. And why did I write it backwards? That's a great question. If I knew the answer, I'd tell you. The standard deviation of that sample came out to be 9.1 minutes. Yeesh. That's the sample. I mean, that's the standard deviation. Could you imagine some of those saps standing in line for like 22 minutes or something? Ugh. Get some people up here, people. So for Whole Foods, and let's say he sampled, let's just say he sampled a different number because I like to keep things interesting. 13 people. And again, you wrote it backwards. Why, Jay? Because you're weird. That's why. 7.2 minutes in line. Holy buckets. So, 9.1 squared over 7.2 squared equals, I don't know. Make 1.59. Okay. Let's say alpha is 0.05 just for a good time. So I'll just pull up the old chart here just for fun and see what you think. So here's 0.05 is up here. And in my numerator, you notice I had Albertson, so 19 and then 12 degrees of freedom. So 19, which notice is not on here, and 12 is going to put me somewhere in the ballpark between 2.6, you see, and 2.5. You could actually average that and be pretty close. I'm going to call it 2.57 or something. Okay, that's what we had to do back in the old days. 2.57. Wait a minute. Are you saying that my critical value over here is 2.57? That's what I'm saying. Well, wait a minute. So you're saying that we're in here. That's what I'm saying. So you're saying I should fail to reject. Would that do the same on a calculator? Of course. Okay. And so what we're going to find here again is I'm just going to use the FCDF. That's all I want to deal with. Okay. So again, I only show you that other deal because I think that, what am I doing? Wrong direction, dummy. I think some people find it fascinating to use charts. I don't know. You know, they were better than nothing back in the day, but ugh, kind of a pain in the neck. And then the degrees of freedom for the numerator were 19, and then 12 for the denominator. And this is a one-tailed test only, so whatever this comes out to be is what it is. It comes out to be 0.2. And so because our p-value is bigger than alpha, we fail to reject. Fail to reject. And of course, that means Albertsons is not significantly worse weight time, but for variation-wise, weight time as opposed to Whole Foods. Now, in here, you'll notice that there is, somewhere in here, a two-sample, do you see it, F test. Only the 89s and some of the later model 84s had this. If yours has it, man, knock yourself out. Nobody cares. Okay? So, I'm going to put in that my Albertsons is 9.1. Okay? And here's the thing. Always, when you're doing this, if you want to see if you get the same answer the book has, and I mean number-wise. I don't just mean reject or fail to reject. I mean number-wise. Always put your bigger one in as SX1. Okay? And so if you do it this way, everything you get will be the same numbers we got. You'll still get 1.59. Everything will be the same. Of course, your decisions will still be the same as well. It's not a problem. But what will end up happening if you put it in differently, you'll get different numbers. Then you're like, oh my God, I'm dumb. I screwed up. You're not dumb, and you didn't screw up. Just be careful. So if you put your bigger one on S1, always, and then always do this upper tailed business. Well, don't do upper tail. If it's equals, you want to do a two-tailed test. But if you set it up that way, what you'll get is the exact same value as we got here. So you get 1.59, yes, and then a p-value of 0.2. Cha-ching! Notice that if you do this the other way, and I'll just show it to you real quick, you're welcome to do it this way, but sometimes people will get into here and they'll go, oh, I'll just do it the other way. And that's fine, you can. But what ends up happening is that you get panicked because you get a different number than I did. And then you're upset, and, you know, hate statistics. It's so hard. It's terrible. It's not terrible. You just got to pay attention to what you're doing. Okay? So, there it is. And because I put it in backwards, you see, it's a lower tailed test this time. But you'll see the p-value is exactly the same. But notice how the f's different. This f is different than this f. You will always get the same f as long as S1 is always the bigger of the two. Okay? But your decision should, in theory, still be the same regardless of which way you go. Okay? That's it, man. Hope that helps you.